Welcome, everybody. I'm extremely excited to be here this afternoon in the final talk session before our wrap-up keynote, which I'm personally very excited about. I hope you are too. And I think that over the past couple of days, probably a lot of us have gone to some pretty intense technical programming talks, and I hope to make this talk a little bit of a palate cleanser and try to get us into kind of engage our brains in some playful thinking and maybe kind of think about some fun things like puzzles and video games that are a little bit less intense than some of the programming talks we've seen so far. I will talk about programming a little bit at the end of this talk, but sit tight for that if that's what you're here for. So I'm presenting how to think like a system, puzzles, problems, and programs. And I want to start out by kind of priming your brain a little bit. Hopefully I can hear some audience responses because I'm actually going to ask you for the answers to some things. So I'm going to present to you a class of problems called Bongard Problems. And these were invented by a Russian computer scientist in the 1960s, Mikhail Moiseyevich Bongard, for studying things like pattern recognition. And they were later studied in a thesis by Harry Foundalis, who studied under Doug Hofstadter, whose writing is influential for the title of this conference, Strange Loop. So a little bit of a connection there. So the way Bongard problems work is they show you a collection of examples on the left and a collection of examples on the right. And your job as the puzzle solver is to figure out what rule distinguishes these two sets of examples. So we'll start with a fairly easy one. You've been looking at the slide for a few moments now. Who can tell me what the rule is that distinguishes these examples? I'm hearing some people say triangles. Yeah, okay, so we've got triangles on the left and quadrilaterals on the right. Now, of course, there are some other features of these shapes, the fact that some of them are filled in and some of them are just outlines, their relative size and position within the squares that represent the individual example. But none of those features happen to be the distinguishing characteristic between the two sets of examples. Okay, here is a slightly harder one. I'll give everyone a few moments to look at it, and then don't shout it out. I'll call on somebody to tell me what the difference is in this puzzle. Yeah? White on top of the left. Yeah, so the unfilled shape, or the white shape on the left, is sort of overlapping the black shape, and then on the right, the opposite relation kind of holds between the two shapes. So that's the answer for this. And I'll show you one more example, which again is, I think, for most people, kind of increasing along the difficulty scale a little bit. But I will give you a little bit of a hint, which is that a number of you I know are interested in recursion. So that might be a relevant property to think about with respect to these examples. Now don't shout out the answer. I'm actually not going to give it. So if you would like to think about this for a moment, maybe take a picture of the slide. If you don't quite see it yet, that's cool. If you want to talk to a neighbor and ask them for the answer, that's also totally fine. All right, so if you like these kinds of problems, like I said, Harry Foundalis wrote a dissertation about them and also maintains an online index of Bongard's 100 original problems that took this form, and then also another 100 that he and other researchers developed on their own. Okay, so with that in mind, I'll now give you some of the context for who I am and what I'm talking about here. So I'm an assistant professor in computer science at North Carolina State University, and I started there a couple years ago and began my research lab, which I call Poem for Principles of Expressive Machines. And this is my third Strange Loop talk, sorry, not my third talk, but my third time at Strange Loop. And when I was here in 2013, 5 years ago, as a PhD student, I was giving a talk about linear logic programming. Totally different concept, totally different topic from this one. However, that does inform the kinds of things that I do and we'll be talking about today. I love functional programming, logic, and proofs. My research these days has more to do with kind of applying those things to creative disciplines, so designing tools and languages for things like interactive narrative, video game AI, procedural generation, and system modeling more generally. And lately, I've been really puzzling over kind of what you might identify as the relationship between two subfields of computer science, human-computer interaction and formal methods, or programming languages. And I've been thinking a lot about how we can relate these things on the left, which I'm calling experiential characteristics, to formal descriptions, to mathematical models of a system that someone is interacting with. So what's on the left over here is examples of things like the emotional state that someone might be in when you create a well-designed video game, for example. It's supposed to connect to this psychological idea of flow, where you're doing something challenging, but you're doing it well. Or when you're reading a story, or even perhaps more saliently, in interacting with an interactive narrative, you experience some dramatic pacing and a certain narrative arc that affects the way you feel. Or the lower left example there is Bloom's taxonomy, which relates to education. How does interacting with a system teach us something, not just imbue us with new knowledge, but actually give us new skills that we can go out and apply, for example, programming. And so I kind of call this question, this is like area of exploration, human-system interaction, sort of refined human-computer interaction. I'm using an example of a video game on the right because what the point is here is that there's an actual formal system somehow that we can identify and describe in formal ways and try to identify some relationships between the definition of that system and the way people relate to it and interact with it. So how does this idea kind of correspond or relate to Bongard problems? Well, something that you may have observed is that Bongard problems take a little bit of a different flavor from a lot of standard puzzles or problems. If you're given a problem set in a class or you're trying to solve a problem, a lot of that tends to be you're taught some rules or you're taught some algorithms and you're just going to apply those to the new cases that you're studying. On the other hand, Bongard problems are kind of going the other way around. They're saying, well, here's a couple of examples that, some things that follow this rule, some things that don't, and your goal is to actually identify the rule. So that process might remind you of a few other things that humans and computers each do, typically independently. So things that humans do include hypothesis-driven science, the kind of kindergarten model of the scientific method wherein you make some observations and based on those observations develop a hypothesis and say, okay, well, I think that the rule is this. As soon as you observe something that doesn't follow that hypothesis, then you revise it, right? And you come up with a new hypothesis. Another thing that you might relate to is test-driven development, the idea that before you write a line of code, you give a sort of approximate specification of what you're doing by providing some input-output examples for a program, and then say, oh, okay, now I see how to generalize those examples to the kind of code that I need to write. Other things that might come to mind include example-driven program synthesis, kind of a related idea to if you were Nadia Polikarpova's talk on program synthesis. There's a certain related line of work in which you're actually feeding the synthesis algorithm input-output examples, and then it's trying to learn how to come up with the program that encapsulates the most general version of that behavior. And a sort of similar idea, of course, that's gained a lot of traction recently is data-trained classifiers, giving a certain system a bunch of examples of pairing input data with annotations, and then having it develop a sort of black box model where you can feed it new examples to get new classifications. So my question here is how we can enable humans and computers to best collaborate with one another to do things like this together. So these include things like, how do we design games? It also includes how do we design code editors, interfaces, and programming languages that basically enable this kind of human-computer collaboration. So with that, I can outline how I'm going to talk about that problem. And the first thing that I'm going to do is set up a general theory sort of from cognitive sciences about mental models. And then I'm going to sort of show how you can apply that theory to make sense of a kind of taxonomy of things across a spectrum of puzzles, problems, and programs. And then I'm going to speculate a little bit about how we can do some of this tool design, sort of how we can enable these processes to work better. So let's start here. So first of all, what is a mental model? We throw this word around a lot casually, I think, when we talk to each other. This idea kind of came about from cognitive psychologist or cognitive scientist Johnson Laird in 1983 in a book titled Mental Models, and he tried to identify, okay, like what distinguishes a mental model from just any other kind of knowledge? Well, it is a knowledge structure, but it can critically do two things. It can predict the outcomes of certain situations or actions, and it can explain those outcomes after the fact. And the way it does this, the theory is kind of that we have a miniature version of an external reality kind of living in our thought processes, in our mental simulation. So again, using the example of a level of Mario video game, we can imagine this game. We imagine a version of the level wherein whatever rules we think are currently applying are going to apply forward, and we're going to be thinking about what's about to happen before we see it happen in the external system. So, zooming in on this particular example of Super Mario Brothers, level 1-1, which is a sort of staple of video game design kind of study because it was the first of its kind in a sense. It was addressing a new audience of video gamers who had never seen anything quite like it before, and so it had to establish new conventions. What we now think of as a standard trope, this kind of idea of platformers and collecting coins and so on, developers had to really work to establish the kinds of things that players were seeing for the first time and get them used to this language of jumping around and doing things in a virtual world. So if you're interested in this level in particular, in kind of this design idea, there's a great YouTube video diving into what the designers did to facilitate this convention and kind of get people on board with what you were doing in this game. What I'm going to talk about instead is just kind of the process that someone might go through if they're encountering this for the first time, sort of cognitively. So the first thing you do is you have a controller, and there aren't that many things on it, right? There's like 4 directional buttons and an A and a B. And if you start out in this situation where there's a lot of white space over to your right, and you're facing to the right, so you might think, okay, I'm going to go right. So how can I do that? Well, I'll press the right arrow. That seems fairly intuitive. Okay, Mario's going right. What do these A and B buttons do? Okay, well, A seems to make me jump. Great. So you sort of fiddle around and you get a little bit of a mental model established that there's some directional movement, there's jumping, there's gravity, that kind of thing. And you have established a mapping with the controls. The next thing that happens is you see some little angry mushroom kind of thing appear to the right of the screen, and you notice that it's heading to the left towards you and you're heading to the right towards it. And based on your physical mental model, you might think, okay, well, I'm about to collide with this thing. I don't know what that's going to do. If it happens, then in fact Mario will die and you'll have to restart the level. Oh no, it's not that big a deal. You didn't get very far if that happens, so you just restart and try again. Okay, but now you've added something to your mental model. That's great. Okay, you've learned something that you didn't know before. When I collide with a mushroom thing, I'm going to die. So in the process, you might, subconsciously or not, also make a generalization that, kind of based on this visual pattern recognition idea, that, hey, that thing was shaped like a mushroom and it was bad for me. So I'm going to make a rule. I'm going to generalize what I just saw to just assume that maybe colliding with all mushroom-shaped things is bad. Maybe I'm going to die. Well, the very next thing you encounter is an actual mushroom, and it looks kind of like that. And so if you apply your mental model in this particular case, you might think, okay, well, I'm going to collide with that mushroom. That might make me die. But when you do it, in fact, Mario gets bigger, which is a good thing in the game. So what has to happen is you eliminate the assumption that you had made, this generalization that your mental model made, turned out to be wrong. There was a different mushroom-shaped thing, and it didn't make you die. It made something good happen. So you have to make a finer distinction and revise your mental model to say, okay, well, colliding with an angry mushroom makes me die. Colliding with just a regular mushroom is fine, makes me big. So to summarize and kind of extrapolate this whole process, mental models are a way of simulating external realities in our minds. They make predictions and explanations about what's going to happen when we do certain things to interact, and they generalize from examples. Sometimes those generalizations are wrong, and mental models can be wrong in general, and they can revise upon failure. So I'm currently playing a difficult platformer game called Celeste. That was released this year, which is really fun. But you die a lot. There's lots of spikes everywhere. And it gives you this little message sometimes. It keeps track of how many times you die. And it says, be proud of your death count. The more you die, the more you're learning. Keep going. I love this as a life message, but I also love it. I also like it as it applies to mental models, because actually the fact that mental models can be wrong is not a flaw. It's how they learn. It's how they develop and become in closer alignment with the actual system model that's making things happen. Okay. So let's try to apply this now. We're going to stay in the video games realm and look at puzzles and kind of how they work in digital games. So there's, again, a great YouTube video from a game designer called Mark Brown, who has a video titled What Makes a Good Puzzle? And the very first thing that he establishes is that you can't get anywhere if you don't have sort of good enough mechanics or clever enough mechanics. And he sort of establishes this as the mechanics of the game are your ironclad rules. They should never change, because if they're changing, then your player has no ability to develop a stable mental model, because the things are always going to be changing out from under them, and they may think, okay, well, I may as well just behave randomly because this mental model isn't stable. So you have to have some kind of clever mechanics. And I want to start with this example of a game called Cosmic Express, in which you draw little train tracks on a grid and collect alien passengers and deliver them to little matching boxes, where they will then get out, and once all of the aliens have been delivered to their homes, your train can go on its merry way and you can go to the next level. So that's the goal. You have to establish some kind of goal for the player, and you have to establish a way for them to get to that goal. So again, these mechanics are ironclad. They're rules, and more importantly, perhaps, they're limitations that will never change. And so in Cosmic Express, this includes things like the train tracks cannot cross over one another. Each passenger has to be taken to a matching box. Each train car can hold one passenger, and the passengers will try to hop into any empty car that passes them. So using these mechanics now, we can start to build on them to create kind of, observe the interesting interactions between things that might happen in various configurations of the level designs to set up some interesting challenges. So for example, there might be some kind of unexpected consequences of the mechanics, including like this example where you have a train car going between two aliens. They both try to get in at once, and neither of them can get into the train car. So those are the kinds of things you may not expect as a player at first, but then when you see them, you're like, oh, okay, sure, that makes sense. So then from there, how do you actually develop a good puzzle on top of this foundation? So there's kind of a trifecta of things, like a pattern that you might experience as sort of an experiential property for a player to go through, which is that you maybe make some assumption about how a level works. Then after testing out that assumption, again, this theme of failure comes back. You realize that it's not going to work the way that you had naively expected it to, perhaps because that's how it worked in some previous levels. And you have to identify what the catch is. Why is this level so much harder than what you'd seen before? And then finally, perhaps after struggling for a while, you have a revelation. You have that aha moment, which is when you finally realize how you can approach the puzzle in a totally different way from how you'd been thinking about it before. So to see this in Cosmic Express, you might see this level. This is just a still of the level. You might look at it and say, okay, well, each passenger is right next to a little box of the same color, so perhaps I can deliver the passengers to the boxes that are closest to them. So then you start drawing routes and trying to figure this out. And then you notice this catch, right? So as soon as you try to draw a route that takes a passenger to its nearest box, you block access. So your means of creating a solution, your tracks, are also your obstacle, right? You run into yourself. You sort of trap yourself by encountering a situation where you're blocking off passages that you need because there's just this one track width passage between everybody. So finally, if you fiddle around with it for a while, you may eventually have the revelation that you can kind of, you can take passengers to farther away boxes than the ones that are right next to them. And so one example, one solution might look like this. To undo that, and then, yeah. So then that top left passenger goes down there, and the bottom left passenger goes up there. So the research question here, for me as someone looking at this, is, does this assumption catch revelation pattern? This is kind of a folkloric idea of what it means to be a good puzzle. And, well, does it have anything to do with mental model acquisition? Does it support, if we build this notion into puzzles when we design them, does it support faster or more accurate mental model alignment? So my lab built our own puzzle game that we could kind of take apart and recombine and tinker with to try to set up different experimental conditions to study this question. And we built it in a scripting language called PuzzleScript, which is a lot of fun, especially if any of you are kind of programming language nerds, like maybe some of you are. It's a lot of fun to play around with. It's a sort of DSL for writing two-dimensional tile-based puzzle games. And we built a game that has these little basically, it involves lasers and mirrors and sensors and things like that. So you can spin around the lasers with the yellow corners, or sorry, you spin around the mirrors with the yellow corners to redirect the lasers. The lasers hit the sensors, and the sensors turn on other lasers, which eventually turn on the exit, so you can finally leave. With this basic set of mechanics, we can develop some sort of interesting consequences of those mechanics, and we actually are giving them names. So sort of we name the skills that the player can acquire after they tinker around with the mechanics and learn certain consequences of them. So this is a skill that we call feedback, wherein we notice that if the player toggles a pressure plate and then steps off of it, the laser can actually stay on. And the reason that works is because, well, let's see if I can actually go back to it. So the way that the level starts out, the laser that would hit that right-hand sensor is being blocked by a door, and the pressure plate will open the door. But then once the laser is hitting the sensor actually toggles the door as well. It's a sort of duplicate power supply for the door, so it no longer needs the player to be standing on the pressure plate in order to stay toggled. Okay. So we built we noticed a sort of a couple of interesting emergent mechanics like that, and we developed a sort of concept dependency tree between them, and eventually kind of came up with some more complex mechanics, like this idea of Beamlock, wherein you can, well, I'll show you through the animation, but this is a puzzle that happens to have an assumption and a catch. So in this case, it's kind of similar to Cosmic Express, where you maybe make some assumptions about proximity to where things are, and you see that mirror that you can pick up and move, which you know because it's got a pink line in it. The pink line indicates that you can pick it up, and you think, okay, well, I'm just going to move that over to where it's going to make the laser bounce off the next mirror, and then I'll go and pick up that splitter over in the top right-hand corner and see what I'm going to do with that. Okay, well, I can bring it down and reduplicate sort of that beam, so now I can move my mirror away, but oh, I can't use my mirror to do anything useful because it's not pointing the right direction for me to redirect it into that sensor that I need in order to open the door. So the revelation is that you can actually use these mirrors and splitters in the opposite configuration from what you'd initially assume. So if you go pick up the splitter, use it in the place where you would use the mirror, put the mirror where you would use the splitter, then you can use the splitter and its more awesome splitting capability to open the door. So after building this, what we wanted to do was to try to kind of ask people if they could make predictions and explanations about what was going to happen in these levels. If you remember, that's what a mental model does. So in order to measure people's mental models, we thought, okay, well, we need to ask people for what they're going to predict something, what they predict is going to happen in a given level, and then let them play it. And then after they've played it, maybe something happened that they didn't expect, and can they explain the discrepancy? Can they show some kind of revision of their mental model after that process? An interesting note that I think is a sort of false start with the study design for this, but which is, I think, relevant to some of the takeaways in this talk, is that we tried initially to give people a think aloud, to just kind of put them in front of the game and ask them to make predictions and explanations before they did something in the game, but they had the game in front of them. And this did not work at all, because if you give someone a thing they can tinker with, and you ask them to tell you what you're going to do next or what's about to happen, they're just going to start pressing the buttons. You cannot actually get them to pause and talk to you. Like I say, there's an interactive thing in front of them, and I don't know yet. I just want to poke things and see what happens. People get very exploratory, which I think is it's like kind of an awesome thing about humans, and that we should like be exploiting more in our designs. But nonetheless, we wanted to get their actual kind of capture their mental state before they had the ability to act. So we just showed them a screenshot before we allowed them to play in this study. So that eventually, because I'm a computer scientist and not fundamentally a cognitive scientist, my research goal is to use what we learned about mental model formation in the study, which we're still analyzing the data for, and eventually maybe procedurally generate puzzle sequences that could support this notion of deep mastery that a lot of us find really satisfying when we play a well-designed puzzle game. So that brings me to the next step of this journey, which is problems. And sticking within the digital games category again, I'm going to show you a couple of examples of what I think of as sort of a different class of puzzle-solving games. And sometimes these are called strategy games. Sometimes they're categorized under puzzles. But things like Infinifactory or Factorio, which incidentally both have sort of factory as their roots, because what you're doing is taking raw materials and assembling them into machinery that can produce new materials, and then sort of recursively building up your infrastructure in order to solve certain challenges. Personal favorite of mine, this is a 1993 kind of version of this, The Incredible Machine, which I grew up with, so this is another example where you're given these kind of goals in order to, you have to make something happen in the level, and you've got your primitive elements or things like things like pulleys and boxing gloves and fire and there's all this stuff that is simulated by the physics engine, which you then assemble together in an elaborate Rube Goldberg machine in order to accomplish the goal. So Mark Brown again has another great video about this distinction, which I find really useful, wherein he talks about puzzle games being in a different category from problem-solving games, because in puzzle games, what you're doing is more like discovering the solution, and in problem-solving games, you're inventing a solution. And there's, of course, two words of difference there, discover versus invent, D versus A. So in a puzzle-solving sort of scenario, what you're doing is essentially, I like to think of puzzle games as a two-player game between you and the designer. It's just that the designer's not there. But they've left you little secret messages in the design of the level of the puzzle. And it's your job to sort of discover those messages, put them together, and kind of make sense of what they intended you to do in this very delicately handcrafted way. Whereas in a problem-solving game, if the game designer is giving you a challenge, they've probably solved it themselves, but it might be a much wider space of possible solutions. And they may not have explored that space very thoroughly, and perhaps they're just waiting for you to find a more efficient solution than whatever one that they managed to find. And so there's a lot more of sort of a process of invention going on, in addition to the bigger solution space. This comes about as well in open world games like Minecraft, where you have materials like redstone, which is essentially a simulation of conductive material that can be used to assemble computers. And you've also got some just kind of more literal interpretations of this idea, like TIS 100, wherein the challenges are to literally write code to a fictional assembly language in order to solve challenges. And there's also kind of a sandbox mode where some very industrious people have decided to re-implement Pong using this fictional assembly language. So of course the question comes about, if we're giving people these things that are literally programming, and we're giving people games that they enjoy and are learning how to build robust mental models of fictional programming language in a game, well, couldn't we also use this to teach computer science or to kind of get people excited about the idea of programming? And there are some folks in the lab adjacent to mine run by Tiffany Barnes at NC State, the Game to Learn lab, who have taken that idea seriously and developed a game called Bots, wherein the whole mechanics are to write a script for a little robot to navigate a 3D world in order to navigate to an exit. And you've got the actions that the robot can carry out, like movement and picking things up. And you've also got looping constructs and variables and so on. And you can challenge yourself in terms of the efficiency of the solution or the code size of the solution. Another example of this that I personally enjoy is this game called Cube Composer, developed by, I think, an independent developer, David Peter, which teaches some functional programming idioms wherein you've got a palette of possible transformations over on the left, and you drag them over to the right in a particular sequence to transform a row of stacks of cubes from an initial configuration to a goal. So that takes us back to, if we zoom out a little bit, back to programs and the question of whether what we're learning here about interaction, failure, mental model construction can just literally apply to the process of writing programs in the wild. So at this point, I've kind of started to sketch out a spectrum, right? On one end, we have puzzles, as you would find in a digital puzzle game, which have a small and very intentionally crafted solution space. You've got towards the middle of the spectrum designed problems, which could include problems in a problem-solving game, or perhaps problems in a computer science class that you might be taking, wherein the solution space is kind of co-designed with the problem itself, like maybe the designer of the problem doesn't necessarily have the solution in mind first. And then finally, you've got kind of open programming in the wild, wherein you have a big solution space, nobody has designed the problem for you, you've just got a real problem that you have to solve, and it precedes the solution. So sort of inspecting these things as all points along a spectrum, we can sort of start to identify some correspondences, like the idea that maybe the mechanics of a game, this idea of having a robust mental model that never changes of the principles underlying the game on top of which you can build more problems, corresponds to having a good mental model of the programming language itself. The puzzles that you can build on top of that set of ironclad rules are sort of like the programming problems that arise within a certain language, and then the puzzle solutions are, of course, the programs written in that language that address the problem. And just to draw another related analogy, you can even think of the whole process itself as going back to this idea from the beginning of learning rules from examples, of sort of designing abstractions that take particular examples and extrapolate them to something a little bit more general. So I actually would like to thank Simon Peyton-Jones for giving me this slide. So this was from his morning keynote yesterday. It's a perfect example. This was a beginning programmer who realized that she could replace a bunch of repetitive steps in a program with a simple loop. So this process of abstraction is exactly the same idea of translating sort of pattern matching, being able to identify, okay, I can represent this in a more concise way. Now, people have actually done a lot of research on how people develop mental models when they're learning how to program. I'm not going to talk a lot about much of this research. It's definitely out there and has been since the 70s. So people are still kind of learning about this, but there was some sort of controversial research that tried to conflate the idea of being able to form robust mental models with the idea that there are people who fundamentally would never be able to program, which they later retracted because, of course, that's nonsense. But the idea of being able to form robust mental models is still applicable. And so a lot of people have done some follow-up research on that, which I encourage you to look into if you're interested. These slides will be posted after the talk, by the way. In reality, of course, most of us are coding with an incomplete mental model of our language. So if you don't believe me, look up Gary Bernhardt's WAT talk, which takes some of our, perhaps your favorite programming languages and shows you that the models that you have of them don't always correspond to what they actually do. So we're coding with an incomplete mental model, but nonetheless, we can get by, right? We can still get things done. And in fact, most of our bugs come from a poor alignment between the mental models of our domains, what we're actually trying to represent, and the program that's supposed to implement that understanding. So that finally brings me to tools for thought. So, I see. Okay, it's counting down now. Okay, so finally, I want to ask this question of is it possible for us to build tools that communicate our mental models directly to a system? So I would argue that in some ways we actually already do this. So whenever we write tests, this is exactly a way to say, here are some examples of what I think my input-output should be for this function count O's. Each test is a communication of the mental model. We also write tests for exactly the same reason we want mental models to fail early. We want tests to fail so that they fail now rather than in production. Type annotations are another way of being able to express our mental models to a system. We might take a look at those examples and generalize to say, hey, all of the inputs are strings, all of the outputs are ints. I would like that to always be the case, and so I will encode that as a part of my mental model that the system can check for me. Whenever we have fancier types, we can give more precise communication of our mental models. For example, if we had a dependent type system, we might be able to say that the value returned by count O's should always be a number that's between 0 and the length of a string we passed in. That then brings us to this concept of like, well, if we can express our mental models in this computationally understandable way, can we use tools to directly run our mental models as programs? And this inspires a whole field that I like to refer to. I think this is Amina Torlock's language of solver-aided tools for things that, for things like program synthesis that can take a specification, a logical description of what we think our code should do, and just produce the code that actually does it without us having to write the code and then check it against the specification. I personally work on a lot of tools that fall under the umbrella of procedural generation, and you don't have to read this code, but it's a logical specification of some constraints on generating a dungeon for a sort of dungeon crawler video game, and so it just takes this logical specification and spits out a playable game level. So do these things really let us directly run our mental models as programs? I find that in practice, no, because then they get big and it's hard to tell whether they're correct. So we've just sort of reduced it to a new problem, wherein we've now created a very generative system that has a whole big space of solutions, and we need a way of navigating that space of solutions and identifying whether or not it's what we expected it to be and potentially changing it. So finally, I'll wrap up with this idea that I've recently learned about from David Krakauer, which I find immensely useful when it comes to talking about the kinds of systems I would like to see more of in the world. And it's this concept of cognitive artifacts, and particularly a distinction between complementary and competitive cognitive artifacts. So a cognitive artifact is anything that helps us think. It doesn't have to be a real physical artifact. It could be a mathematical system like Roman numerals or multiplication tables, or it's a system of calculus, right? But it's something that helps us think. And a competitive cognitive artifact is something that enhances our mental abilities as long as we have it with us, but as soon as we discard it, we no longer have that ability. So something like a calculator falls under that category. On the other hand, a complementary cognitive artifact is something that gives us new abilities, but we can actually internalize those abilities. We've gained something new from using the artifact, and therefore when we discard it, we may not be as fast or as accurate as we were when we had the artifact, but we still have the ability we have this mental model that is left behind that we can run to simulate what abilities it gave us in the first place. Another example of this for me was actually the same artifact, but used in two different ways. GPS navigation as a driver, where you're getting something that's telling you verbally, kind of what to do at every turn, versus when you're using it as a passenger or as somebody walking around, kind of looking at a map and seeing where you are. You get a very different sense of the geography around you and of how you fit into kind of a city and a built environment as a system when you use these systems this way. And in the case where you're using GPS just to navigate, through voice commands, you're not getting a coherent map of the place where you're navigating that you can then use and apply after the GPS turns off. Just again, to tie this back into games, I think augmented reality games like some of the Niantic games like Pokemon Go and Ingress, which preceded it, are another example of a complementary cognitive artifact in this space that actually changes our relationship with the systems we're a part of, that can give us a new view and kind of teach us new things about the world around us. So the takeaways here, and I'm just about out of time, are that automated systems that are really at their best. Automated systems are the most awesome when they help us develop mental models and facilitate us as human beings so that we can collaborate better with them. However, not a whole lot is known about how to do that. So if you are interested in furthering this research mission, I would definitely invite you to collaborate with me if anyone is potentially interested in applying for a PhD. We do have a program for that at NC State, and I'm also willing to talk with potential faculty and industry collaborators. So here's my contact information, and thank you very much.